It's a privilege and a pleasure to be here in Aberdeen. My first time in Aberdeen, actually. Okay, so here's the man, John Dunster, my parents' generation. My parents were born within a couple of years of that. I knew him in the last years of his life, a nice guy, when he was working down and living down in Oxfordshire. And I just thought that I'd spend some time looking at some of the things that John Dunster did. Just a few of the papers that he wrote. You'll see that he was an author of a paper in a very early volume of JRP. Was also writing in Nature, the big fuss that occurred over the idea that irradiation of fathers could increase the risk, but substantially increase the risk of leukemia in children, so he's involved in that. And you'll see here also looking at the history of and policies, procedures of ICRP, and with Jack Valentine, who's there he is down there, yes, who's actually here today. Some of the other things, of course, he was involved a lot in discharges from Sellafield, collective dose. He got involved in the collective dose arguments, writing an editorial there. And just the year before he died, looking at what were then the upcoming recommendations of ICRP and the discussions that were surrounding that. Of course, the recommendations were actually published the year after his death in 2007. But I just want to dwell on one of the things that was a sort of baptism of fire for him, I guess, which was the Windscale reactor fire, the Pile No. 1 fire in October 1957. And John Dunster was heavily involved in the fire and the reporting afterwards. And here's just a couple of the papers that he was an author of with Hugh Howes and Bill Templeton in a UN conference, which is the JRP published on the 50th anniversary of the fire, and also in Nature with Arthur Chamberlain writing up what was going on. It was, and of course, when you look back now 60 years, this is the 60th anniversary of the fire. You have to remember that this was a different era. The past is a foreign country. They do things differently there. And indeed they did. This was Windscale Works in the 1950s, built principally to produce weapons-grade plutonium in the two Windscale Piles at the back here. And here's the reprocessing plant where the plutonium was extracted from the irradiated uranium fuel. It also produced other materials, but there it was in the 1950s. And here's the Windscale Piles, and in October 1957, the reactor in Pile No. 1 caught fire, and the activity was emitted from the 120-meter high chimney, and was readily detected in the surrounding area. Before the fire was actually put out by Tom Toohey turning on fire hoses and flooding the reactor, which was a pretty risky operation. Again, past is a foreign country. This was the incident control room, which looks rather primitive these days, but that's how they dealt with the immediate consequences of the fire in those days. And the monitoring that was taking place in the vicinity of Sellafield was finding significant quantities of iodine-131 in milk. But the health physicists at that time were faced with the circumstances that for this type of environmental contamination, there was in fact no agreed recollected limit for radioiodine in milk. And in one evening, John Dunster, Andrew McLean, and Reg Farmer performed calculations and derived this limit of 0.1 microcurie per litre of milk. And so they they pulled this together, which was in about an order of magnitude of, less than an order of magnitude, in fact, of what we would consider today to be a limit of 131, iodine 131 in milk. It was on the basis of these calculations that John Dunster was involved in that a milk distribution ban was immediately established in the worst affected area around Sellafield in West Cumbria. That limit that they'd pulled together led to milk restrictions from around about 600 farms in a 500-kilometre square area of West Cumbria, southwest Cumbria. And that ban remained in place for 6 weeks for the worst affected farms close to the site. And that meant that 3 million litres of milk were tipped down the drain, and that the cost was, in compensation, was over, in today's money, over £1 million. So that was quite a tough decision to make. It would have been tougher these days with the media, social media, and all the rest of it. But even then, it was tough in those days. And John Dunster was 35 when these sort of decisions were being made. That, as I say, was a pretty courageous decision, but it was a right decision. And the likes of Chernobyl in 1986 and the consequences of many thousands of excess thyroid cancers in those exposed as children shows that was a correct decision. But as I say, courageous for someone of 35. Oh yes, just while I'm on this, I just thought I'd throw a few slides in here to follow that up. This is Seascale, the village adjacent to Sellafield, and here's the #1 pile chimney. Seascale is where in 1957 many of the scientists and management from the site actually lived, and the radioactivity that was being discharged from the fire was readily detectable in Seascale. But there was no advice to shelter, for example, as I strongly suspect that we would do these days. And indeed, when the water was put on the core at 9 o'clock in the morning of a Friday, which could have caused a pretty big explosion, one might have considered these days evacuating the immediate neighborhood, but people were still getting on and wandering around in their, going about their everyday lives. There was one guy called Frank Leslie who didn't like this at all, who was measuring radioactive deposition in his back garden. He had a young family at the time, and he wrote a letter to the then Manchester Guardian on October the 12th, and again you'll see it's covered in what is the News Chronicle, which no longer exists, and quite a big piece about this, where he's saying, look, there should have been a warning and all the rest of it. This came to the attention of the then Prime Minister, Harold Macmillan, who was involved in some pretty sensitive negotiations with the United States to re-establish cooperation in nuclear matters between the UK and the US. And he most certainly didn't like, well, first of all, he didn't like the fact that an accident had occurred, and he certainly didn't like it that one of the scientists working at the site was kicking up this fuss in the media. And you will find this is actually Macmillan's handwriting. You'll find this in the files. Dr. Leslie must be an opinionated ass, but I suppose he must be seen by 40 million people, Harold Macmillan. And you can actually download that for free from the National Archives. Fascinating file, which is the Prime Minister's file for the Windscale fire. Interestingly, I put this up again in relation to the Windscale fire. This is in the Daily Express. in early November, and it's written by a guy called Chapman Pincher. Some of you may remember, he was sort of an espionage spy journalist who actually only died just recently in 2014 at the age of 100. But he was infamous for all his articles that he wrote on exposing Soviet spies. But it's interesting the way it starts off here. The Prime Minister has decided to publish the report on the atomic accident at Windscale in full, so that he cannot be accused of using security to hide damaging facts from the public. Is that so? Well, in fact, it was exactly the opposite, because it was Prime Minister Harold Macmillan who actually said that the Penny Inquiry report, which was the official report into the Windscale fire, should not be published in full, and that there would be a summary published in the white favour. So you have here an early example of what we would now call fake news, and certainly spin. And I found this, and I thought you might like it. A quote: "The columns of the Daily Express are a kind of official urinal where high officials of MI5 and MI6 stand side by side, patiently leaking. Mr. Pincher is too self-important and light-witted to realize how often he's being used." Of course, it wouldn't happen these days. Actually, I think that's doing a disservice to Chapman Pincher. He knew that he was being used on occasions, but it was a balance of the stories that he actually got, and he got quite a few stories. But I thought you'd like that. I think before I pass on to the meat of my talk, we should just recall that those who cannot remember the past are condemned to repeat it. I think that the Chernobyl and Fukushima accidents were indeed preventable, and perhaps we should remember the past a bit more. Okay. Risk of low-level exposure. The main theme is there a risk of adverse health effects such as cancer following low-level exposure to ionizing radiation? And if so, are we using the right estimates currently in radiological protection? Now, I don't think there's any rational dispute. It's beyond reasonable doubt that exposure to moderate and high levels of ionizing radiation increases the risk of stochastic effects, in particular cancer in the exposed individual. The evidence, both epidemiological and experimental, is overwhelming for this, and the IARC class this as Group 1, the International Agency for Research on Cancer as Carcinogenic to Humans, no doubt about it. The question then is, what do we do about low-level exposure? And at the moment, we look at the nature of the relationship between exposure and disease at moderate to high doses, and these are mainly external gamma or X-ray radiation, which are experienced briefly. And then you combine that knowledge of moderate and high doses with an incomplete knowledge of biological mechanisms. Unfortunately, we don't have sufficient knowledge of radiobiology to be able to say in principle what the risk is from low levels of exposure. And this is a schematic of what various dose responses might be. Here you have at moderate high doses with the various schematic data points from epidemiological studies, giving you a reasonable idea of what's going on up at these levels. But here's the problem down here. You can have various dose responses fitting these data up here, but they do very different things down here, from the linear extrapolation right down a threshold. Even hormesis, that slight radiation might be doing you some good at low levels, and these superlinear curves up here. And the problem is that those who support these sort of more extreme dose responses tend to hold these opinions very strongly and shout very loudly from the wings at people like ICRP, whose job it is to to formulate recommendations on radiological protection, which really doesn't help matter. The conventional approach adopted by ICRP for purposes of radiological protection is that for low doses, where that's conventionally defined as less than 100 milligray of sparsely ionizing radiation, or, and it's important to have that or, a low dose rate, and that is less than 0.1 milligray per minute of sparsely ionizing radiation averaged over about an hour. So it's around about 5 milligray per hour. The excess risk of cancer can be directly proportional to the dose received with no threshold dose. And this is, of course, what is referred to as the linear no threshold, LNT, dose-response relationship. And that underlies the system of radiological protection that we work with today. I just divert just to hopefully remind you, but certainly to dwell on measures of risk, which you'll see on some of the slides that are coming up. They have fancy names, but in actual fact, they're very simple. There's the excess relative risk, ERR, and it's just the proportional increase in risk above the background risk. That's all it is. And then you have the excess absolute risk, which is just the additional risk sitting on top of the background risk. And you will appreciate that you can have a large proportional increase with a small background risk to produce a small additional risk. So these measures of risk can provide very different indications, and that's just a schematic. Here's the background risk that you would experience anyway without additional radiation exposure. The red is the additional absolute risk as far as exposure to radiation is concerned. So the excess relative risk, the proportional increase is just the red over the blue, the proportional increase in risk, and the excess absolute risk is just the red, the additional risk sitting on top of the background risk. That's all it is. Right, where do we get our information from the exposed populations? It's these. It's Japanese bomb survivors, those exposed for medical reasons, those exposed in the workplace, and those exposed in the environment. The bomb survivor studies are immensely important, the two atomic bombings of Hiroshima and Nagasaki in August 1945. A lot of work has been dedicated in the study of the Japanese survivors of the atomic bombings, in particular the lifespan study, the LSS, and that's around about 86,500 survivors who have dose estimates. Some of them don't have dose estimates because of the situations that they were in. It's very difficult to actually accurately estimate the dose. 48,000 survivors were non-trivially exposed, so doses greater than 5 milligray. But again, although the LSS, the bomb survivor studies, are usually thought of as high-dose studies, 2/3 of these survivors who received non-trivial doses actually received doses of less than 100 milligray. So conventionally, these are low doses, so 2/3 of them. So they do provide quite a bit of low-dose information. As I say, it's a very impressive study, the LSS. Started in 50, going now. Lots of work done on the doses they received, individual organ doses or tissue doses, mortality and cancer incidence. Very impressive study. And this is what mortality from solid cancers, essentially cancers other than leukemia, looks like from the latest follow-up. So that is 1950 to 2003, and you can see there's a very nice, essentially linear dose response. But of course, going up to high doses. The problem is, this is the area that we're going to be interested in for doses of less than 100 milligray. And of course, that's way down there where there's a lot of statistical noise, and it's difficult to discriminate or tell exactly what's going on. All isn't necessarily lost, however. This is a plot worked up from that last follow-up. So that is the proportional increase in risk for doses going up to half a gray. And this is the dose response you get from way up here going to moderate to high doses, and these are just sort of a moving average, if you like, smooth moving average. And even if you go down to these low doses, the linear dose response still provides a reasonable description of what's going on down here in the low doses. You eventually, of course, lose statistical steam at about 60 milligray, and statistical significance is lost. But nevertheless, that's reasonably reassuring that you're not, from the bomb survivors, not far out in this low dose region that we're principally interested in. Okay, so then we move on to those exposed for medical purposes. And a lot of these are irradiated for therapeutic purposes, so they're by definition high dose exposures, particularly now, of course, with the increasing survival of cancer patients, more opportunity to see what the effect of radiotherapy might have had on those patients. And increasingly now, because of CT scans and other diagnostic means, diagnostically exposed patients who, of course, are exposed at low doses. There have been a number of studies of those exposed for diagnostic purposes up to now, and they do indicate that around about 10 milligray of X-rays can increase some cancers. There were a group of tuberculosis patients in North America treated with collapsed lung, and they were given a series of X-ray examinations. Then there are scoliosis patients, curvature of the spine patients, again given a series of X-ray examinations, and both of those have an increase. Female patients have an increase of breast cancer, which is proportional to the number of examinations they received. So again, indicative of that low doses can increase at least some cancers. And then you have these old case control studies where antenatal radiography is associated with an excess risk of childhood cancer, in particular of childhood leukemia. Then you're again looking at doses to the fetus of about 10 milligray of X-rays. So some indication from studies that have already been performed several years ago now that there is an increased risk from these low doses. And of course, what we have now, and other scanners are available, is a greatly increased use of ionizing radiation in diagnostic medicine, to the extent that an average citizen in the USA now receives more radiation from medicine than from background radiation. And that's a dramatic change from, say, 20 years back. And we are now getting to see some of the early studies of CT scans. This is one by Mark Pearce and his colleagues, and it is looking at patients in Great Britain who were exposed as children or teenagers, and then followed it up and linking into the big cancer registry databases. And you can see that this is for leukemia, and it's the relative risk, so that's just the excess relative risk plus 1, so this is 0 risk going along here. And you can see that there's a significant dose response for leukemia. And this risk estimate here, the proportional increase in risk per unit dose, is about what you'd expect from the atomic bomb survivors. So again, a series of low-dose exposures looks to be increasing at least the risk of leukemia when the exposures occur in childhood. However, you have to be very careful about interpreting the studies of medically exposed groups, because they certainly form a valuable complement, and indeed the studies of the British ankylosing spondylitis patients back in the 1950s was the first confirmation of excess risk of leukemia that was being seen in the bomb survivors. So they're a very valuable set of studies. But the exposure occurs because of a known or suspected disease. That's what you're doing it. If it's a known disease, it's radiotherapy. If it's a suspected disease, it's diagnostic exposure. And that causes problems because you're not, as in the case of the bomb survivors, they were in the wrong place at the wrong time. They weren't being irradiated because they were ill. They just happened to be wandering around in Hiroshima and Nagasaki. Not the case with medical patients. And you have this thing called reverse causation or confounded by indication, so that you may be carrying out CT scans, the disease is already there, but is only manifest later on, but it is the disease that is causing the CT scan, not the CT scan that's causing the disease. So that is known as reverse causation. There may be predisposing factors to certain cancers. Those predisposing factors may cause that individual to have more CT scans than otherwise because of the other things that these predisposing factors produce in the individual, and that's confounded by indication. So, and I'll give you an example of that, possible example of that in a minute. Radiotherapy, of course, involves high and localized doses to kill disease cells. It also inevitably kills healthy cells. That can lead to problems in working out risk estimates. Obviously, usually anyway, therapy is highly localized, and then you have scattered doses of the rest of the body. So accurate doses are difficult, sometimes lacking. A lot of work is being done to reconstruct doses from these now. And here is a potential example of the problems of reverse causation or confounded by indication. Not necessarily, but possibly. The same British CT scan study that I showed you earlier for leukemia, this is the same thing for brain tumors. And this risk, this risk coefficient, the proportional increase in risk per unit dose, is rather high in comparison to what you'd expect from the atomic bomb survivors. And so you say, well, you know, why are these children being given head CT scans to get these brain doses? And in particular, how come that these children are being given head CT scans so much that they have brain doses over 100 milligray of X-rays and up to 300 and beyond? Is there something wrong with these children anyway? Is this reverse causation? Is this is confounded by indication? So these are nice studies to do, but you have to know a lot of details to be able to properly interpret them. This may be right, but there are questions to be answered. However, there are some very good studies coming along now. This is with Jay Lubin that is just going to appear in the scientific literature. This is a big pooled analysis of thyroid cancer after irradiation for a variety of reasons. It includes the bomb survivors, but also those irradiated for medical purposes. And you can see that we're talking about radiation doses here of 200 milligray. This is just this bit here blown up. For thyroid cancer, at least, there's a very nice linear dose response going all the way back down. And in fact, you only lose statistical significance at about 40 milligray of X-rays. So, you know, these are exceptionally useful studies. And because this is thyroid cancer, just goes to show that John Dunster was right all those years ago in getting the milk banned. Environmentally exposed groups, another useful lot, but need to be interpreted very carefully. High natural background radiation, radon of course, but there's also areas of the world with external gamma, weapons testing fallout, and contamination. Chernobyl, of course, with thyroid cancer because of the radioiodine that was coming out, and the Techa River, which was heavily contaminated by the Mayak plant, which just dumped its highly active raffinate in the river. And so there are opportunities for those to study those exposed in the environment. Here's one opportunity. This is Kerala in southwest India, and this is interesting because there is exposure on the coast here to mainly on the coast anyway, to monazite sands. These are thorium-bearing sands, and this leads to quite high levels of external gamma radiation along the coast there. So a lot of effort has been expended in studying the populations in Kerala who have been exposed to these high levels of radiation over their lifetimes. And a lot of effort has been expended in producing a local cancer registry, for example, for the purposes of following up these individuals. But you always have to be extremely careful. I emphasize again, and this is in a different context. These are homemade cigarettes that are smoked down in India. And one always has to ask, if you're comparing a population on the coast, which is the highly exposed population, with a population inland, are there background differences in those populations? It's not just a question of comparing the high exposure with a low exposure with similar populations. One may be a fishing community, one may be a farming community. Does that affect their background risk? One always has to bear in mind the possibility of this confounding entering in. However, here's what the risks look like in Kerala, following up these populations. Hardly any information at all of any use coming out of leukemia, because there's too few cases. But you can see that for cancers other than leukemia, and again, this is the proportional excess relative risk +1, so here's a zero risk. So not much indication there of anything going on as you're going up into the high levels. And of course, this is a chronic exposure to higher levels of radiation. And just blowing up that plot, it's getting quite interesting, because here's what you get from Kerala, the background radiation study, and here's a comparable population from the atomic bomb survivors. And you can see that although these two populations are producing compatible risk estimate, they're starting to become incompatible, in that you would expect the Kerala population to be higher here rather than showing nothing at all. So interesting to follow up, but be careful, because you've always got to look very carefully about these populations. And here's another opportunity. We know from the bomb survivors and other exposed groups, medically exposed groups, that childhood leukemia is particularly susceptible to radiation induction. And indeed, if you do a big enough, and they do have to be big, if you do a big enough study, then the models do predict that you should be able to detect the background, the effect of natural background radiation upon the risk of childhood leukemia in this case, it's in Great Britain. And indeed, the preliminary results of the study that was carried out by Jerry Kendall and his colleagues do indicate that there is a statistically significant dose response for childhood leukemia, which is a wide confidence interval, but that is compatible with what we would predict from the atomic bomb survivors. But you don't see this for childhood leukemias other than, childhood cancers other than leukemia. Again, you wouldn't expect that in current models. So that's interesting. But again, a lot of work needs to be done, because these are not easy studies to do. Finally, then, there's exposure in the workplace. We have a whole raft of workforces to look at. Of course, our radon risk estimates principally come from the underground hard rock miners, uranium, tin, iron ore miners, and various others, radiologists, aircrew. But a lot of work is now being done on nuclear industry workers, UK and North American, but that's spreading out to other countries like Japan and France. and the former USSR, which I'll come to in a moment, in particular the Mayak plant. And here's a jolly set of Sellafield workers. And why do I show this? For three reasons. First of all, they are a healthy bunch, and you see that in their rates. In general, nuclear workers, along with other workforces, and nuclear workers are not unique in this respect, have lower mortality rates than the general population, because you don't employ the chronically ill and all the rest of it. And so you must take that into account when you do the studies. The second point is that the nuclear workers have good personnel records. And that's very important if you want to link into these big national databases. If you have a John Smith and nothing else, you'll find lots and lots of John Smiths in the national databases. If you have a John Willard Smith and with a date of birth, that makes life a lot better to actually get the right person in the death registers or the cancer registries. So it's important to have these have these personnel records. And then they carry around a lot of instrumentation, which is very helpful because you have prospective dose estimation. Obviously, the bomb survivors were wandering around in Hiroshima and Nagasaki, not wearing film badges, so they had to be reconstructed. These guys, more so these days than in the past, but they're carrying around instrumentation, and that makes life a lot easier to get accurate dose estimates. And these are important groups because they've accumulated these radiation doses over many years. And indeed, some of them, if they worked far enough back, have got largish cumulative doses. Some of them are up to a CVO. But the pattern is many small doses accumulated at low dose rates, and that's important for radiological protection purposes. It's fundamental to radiological protection. So, you know, they provide a direct window into what we are interested in. And you can see this is a sort of typical pattern. This is schematic of the sort of exposure that is being experienced by a nuclear industry worker, for example. So goes into work for 8 hours, wanders around in various levels of radiation field, goes home for 16 hours, back again, and so on throughout the working life. And when we talk about these cumulative doses, it's important to remember that this is the pattern of doses that we're speaking of. And these early sites, here we already mentioned Windscale operation in the 1950s. Here's Windscale's equivalent in the Soviet Union, set up to make Stalin's plutonium, Mayak in the southern Urals of Russia. These sites are important because the early nuclear states, principally the early nuclear weapon states, the doses that these guys receive would not be acceptable in these days. And some of these guys, as we shall see, have accumulated reasonable doses over their working lifetimes. And that's useful because, you know, the high doses, reasonable doses, you stand a chance of detecting any risk that there might be there. And they're also, if you've been working there in the 1950s, the chances of you're now being dead are pretty high. So the data are coming in. And you can see this in doses for Sellafield workers, males and females, and the annual doses, the mean average dose being received by workers at Sellafield over the years. And you can see that in the 1950s here, you're talking about average doses of 15 millisieverts, right, by these workers. And of course, it comes down, and it's way down here now. But these early guys offer an opportunity to really see if there's any radiation-related excess risk of cancer there. And the latest studies that have been done are the INWORKS studies, the International Nuclear Workers Study, INWORKS, and that includes at the moment workers from 3 countries. And the importance here is that these countries are early nuclear countries, early nuclear weapons countries. So they will include workers from sites who will have accumulated pretty reasonable doses. Again, these are guys from the early years, so many of these will now be dead. So we know about them, the data is in, as it were. And you can see there that that we're looking at about 1/3 radiation workers included in these studies. So these are big studies. You know, these are average doses, so you know that's not bad. Again, 18,500 workers with cumulative doses greater than 100 milligray, and 20,000 cancer deaths. But of course, these sort of doses were accumulated over years, sometimes many years. You remember that pattern of exposure. So these are not acute doses. That's the important thing. 20,000 cancer deaths. So these are the results that have just been published in the last couple of years. This is looking at leukemia, excluding chronic lymphocytic leukemia, which is more like a lymphoma, so is usually excluded from leukemias when you do the analysis. And you can see that here is a statistically significant dose-response relationship for leukemia, with doses, as you see, going up here to half a gray or so. The interesting thing, of course, is how does it compare with the atomic bomb survivors? And there in green is the studies from the results from the equivalent lifespan studies, so that's adult males. That's not bad statistical compatibility between the two. For all cancers except leukemia, again, a significant dose response for these cancers. And again, how does this compare with the lifespan study of the atomic bomb survivors? And there it is. A more powerful study, at least for the time being, is the atomic bomb survivor study, so narrower confidence intervals. Interesting that this is lower, or at least the INWORKS dose response is higher than one might expect from the lifespan study. So reasonable compatibility, which adds reassurance to the ideas the idea that we're not getting radiological protection at the low levels of exposure dramatically wrong. I would, however, as I have with the medical studies and the environmental exposure studies, issue a couple of words of caution about these studies, because they do need a lot of work. And that work has only been done not completely at the moment. I mean, I was going to say to a limited extent. That's not fair. But there are questions to be answered. For example, what I've just shown you there, those INWORKS results consider only photon doses, mainly gamma doses, of course, not neutron or internal doses. And then there's this question which I've raised before now, of early missed photon doses. And when I talk about missed photon doses, I'm talking about the likes of film badges with high limit of detection, which are changed frequently, as they were back in the 40s and 50s, for example. And they are recorded as zero dose because you get a dose, but it's below the limit of detection. You put it down as zero, but you change your badge a lot, and that can hide quite a lot of missed dose. And what I've shown here is for the Hanford site in the USA, in Washington State, and the Savannah River site. These are the actual recorded doses, the lower ones here, these two sites, for the purposes of compensation, worker compensation in the States. These are the doses that are actually incorporated in that compensation scheme, which take account of the possibility of missed doses, as I was talking about, the high limited detection. So how do these, if such things exist as a problem for INWORKS. How does that affect the excess relative risk estimates that we've just been talking about? If there is a positive correlation between the recorded photon dose, the photon dose that's actually used in those studies, and these other doses, including the missed photon doses, then it will lead to an overestimation of the slope of that dose response that we were looking at. So that should be lower. That's what that would mean. But that's a big if. We don't actually know if that's right or not, then that's still to be investigated. So these studies of workers are very useful, undoubtedly. But you have to look into them very carefully indeed. And you can just see how useful and what sort of information is still to come from the workers by looking at the National Registry for Radiation Workers in the UK. And this was the latest reported results from Colin Muirhead and his colleagues. And that takes the follow-up, so cancer deaths up to the end of 2001. And this is what this is how the numbers distribute with the lifetime doses. And you can see that there are about 10,500 workers in the UK who had a cumulative lifetime dose of radiation in excess of 100 millisieverts. And they actually carry with them a lot of the information. But in this study here, only a quarter of these workers had actually died. So you have 3/4 of those workers still to contribute to the information coming from these studies. So there's still a lot to come out of these studies, and in particular the international worker studies. There's a lot to come. So just to conclude then, we can expect a growing evidence base for low dose or low dose rate effects. So less than 100 milligray of low LET radiation or less than 5 milligray an hour low dose rate. CT scan studies that we looked at, the natural background radiation studies, I've just looked briefly at a couple of those. The radioactive contamination studies that I haven't had time to look at, but an awful amount of work is going on to follow up the riverside communities in Russia who lived alongside the Techa River when highly active raffinate was just pumped straight out of the Mayak plant into the river, and some of whom got pretty high doses, and also took in quite a lot of strontium-90, for example. And then we have the radiation worker studies that we've just been looking at. These are very, potentially very useful sources of direct information on low-level exposure. But, the big but, these studies are difficult to design, conduct, and reliably interpret. You know, one cannot get away from that. For the reasons, some of which I've pointed to in this talk, there are real difficulties. They can be got round. These are not easy. I think we can conclude there is some evidence of some excess risk of some cancers following low-level exposure to radiation. And you'll see that I've been very careful. Not all cancers, some cancers. But there are indications there that there are some excess risk at low doses. But so far, the epidemiological evidence does not indicate that there is a material deviation from the LNT model, from the linear no-threshold dose-response model that forms the current basis of radiological protection. It's just not persuasive at the moment that we've got a big deviation, either that we've got a threshold dose or that we're dramatically underestimating the risk from low levels of exposure. At the moment, the LNT model is the most scientifically parsimonious, description of the available scientific evidence, and therefore it is prudent to retain the LNT dose response model for the purposes of radiological protection until reliable evidence for any alternative model emerges for the degree of risk at low levels of exposure. And note reliable. And you can appreciate, I hope, from some of the difficulties that these workers, that these researchers have in doing these studies properly, just how important that word reliable is. And that's it. Thank you very much.